Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at the dreaded buffer calculations, but in this one we're not working out the pH of the buffer. We are having to work backwards from the pH to figure out the mass of salt that we would need to add to the weak acid in the first place to make the buffer. Now, in some ways this might be considered a worse question than working forwards to get the pH of the buffer, but I would argue if you can do the calculation forwards, then you can do the calculation backwards, because we're going to be using the same Ka expression. We're just going to need to rearrange it a little bit differently, and if you understand here how to do it forwards, then you can kind of piece it together in your head how to go backwards. And also with a question like this, if you do look at it and go, oh my gosh, I've got no idea where to start, there are two things that we can get marks for in this question, which is going to be converting pH into H plus and pKa into Ka, which will get us 2 marks even if we don't know where to go from there. So in that respect, perhaps it's not as bad as you may think when I say backwards buffer question, and hopefully I'll show you that it doesn't need to be feared. That's my goal. So there are 2 ways we can make acidic buffers in the first place. We can, here come the coloured pens, get some weak acid, put it into our beaker, get the salt of the weak acid, put that into the beaker, ta-da, we've made a buffer. And that's exactly what we're doing in this question. We are trying to work out the mass of the salt that we need to put into the beaker with the weak acid to create a buffer with a certain pH. Okay, so the weak acid that we're using is methanoic acid, and the salt of that weak acid is sodium methanoate. And they've given us the equation for the dissociation of the methanoic acid so that we can write a Ka expression involving those terms. The goal, calculate the mass in grams of sodium methanoate, of which they've also given us the formula so we can very nicely get the MR, that must be added to 25 centimetres cubed of 0.1 mole per decimetre cubed methanoic acid to produce a buffer solution with a pH of 4.05 at 298 Kelvin, and then we've got the pKa value for methanoic acid. So first thing that I am going to do is the 2 calculations that you can do even if you're not sure how else to proceed with this question from there. So if we already have the pH, we hopefully know that we can do 10 to the power of minus pH to get the concentration of H plus. And even if you don't know whether that's necessary, if that's a calculation you know how to do, it's worth giving it a go. So if I do 10 to the power of minus 4.05, that will get me the H plus concentration, which I get to be 8.91 times 10 to the minus 5. So that's the first thing that I would do here. Secondly, I'm going to convert pKa to Ka. Same relationship between pKa and Ka as there is between pH and H plus. So pKa, no, forgive me, I always get this the wrong way around, even though I know the relationship is the same. So it's going to be 10 to the power of minus pKa will give me the Ka. So 10 to the power of minus 3.75, which gives me 1.78 times 10 to the minus 4. Okay. Both of those I've done to 3 significant figures because of the values in the question, and you can leave your whole calculator display on, or if you write them to 3 sig fig and then use them as 3 sig fig, we should get the same outcome. Okay. And then the third thing that I would do when we're thinking about a buffer question is write out a Ka expression. Now, if we know what the weak acid and salt is, I'd always write a specific equation. So rather than using H plus A minus over HA or H plus X minus over HX, let's do it properly. And we've been given the species that we need in the dissociation equation. So Ka is always concentration of the products, so the HCOO minus, which is going to be the salt. So that there is going to be our sodium methanoate, H plus, and then divide that by the weak acid, which is our HCOOH. And from here, even if we still weren't sure exactly what we needed to do, we can go, I've now got a value for Ka, 1.78 times 10 to the minus 4. I've got a value for H plus, 8.91 times 10 to the minus 5. And I've got a volume and a concentration of the weak acid, so I can either sub in the concentration here, or if you've seen one of my videos before, you'll know that I like to use the moles of the weak acid and the salt. I can figure out the moles from the volume and concentration and have the moles of the weak acid. And it doesn't matter whether you use concentration or whether you use moles. If you sub the concentration in, you will work out the concentration of the salt, and then you'll just have to times that concentration by the volume to get the moles. Or you can put the moles in and you'll get the moles out. And I'm going to use moles because that's what I always do, so for consistency. So when I rearrange this, I'm going to say Ka times, and I'm not going to write the square brackets because I'm going to use the moles of the methanoic acid, divide that by the concentration of H plus, which always has to be the concentration of H plus, and that will then give me the moles of HCOO minus. So then the next thing I can do is work out what the moles of the weak acid are going to be. So moles is concentration times volume, so 0.1 times 25 over 1,000, 0.025. That gives me moles of 2.5 times 10 to the minus 3. And then I can sub those three values in. So my Ka is 1.78 times 10 to the minus 4, times that by moles of the weak acid, 2.50 times 10 to the minus 3, and then divide that by the value for the H plus, which we got from the pH, 8.91 times 10 to the minus 5. That gives me, for the moles of the salt, let me just find it on my calculator, that gives me 4.99 times 10 to the minus 3. And that will be moles because I did the weak acid in moles. Like say, if you put 0.1 in here for the concentration, we'll obviously get a different answer here, which would be the concentration of the salt, and then we do whatever that came out as a concentration times 0.025. I've now got the moles, and if I want to know the mass, then we all know hopefully how to convert between mass and moles. So mass is going to be equal to moles times mR. We can work out the mR from the formula we were given, HCOONA. So the mR I get to be 68. So we're going to do 4.99 times 10 to the minus 3 times by, I should write it as 68.0. All mRs should be to 1 dp. Like so, and that will get me the mass of the sodium methanoate we need to add, which 0.339 grams, which again I've recorded to 3 significant figures because all of the data we've been given up here in the question, 3 sig fig, 3 sig fig, 3 sig fig, 3 sig fig. So the mass, 0.339. Now, if we were working forwards to work out the pH of this buffer solution, we would first of all use the mass and the mR to get the moles of the salt. I would then again use concentration and volume to get the moles of the weak acid. And then we wouldn't rearrange our Ka expression like this, we'd rearrange it to get H plus concentration equals by doing Ka times the moles of the weak acid divided by the moles of the salt, and then as soon as we've got H plus, minus log our answer. And all we've done is do that in reverse. And hopefully you can see that, and hopefully that's made that question feel a little bit less daunting. But please do ask if anything is unclear. If you want to give it a go using the concentration of the methanoic acid to get the concentration of the salt, then convert that into moles to check that you get the same answer as me, please do. And if you don't and you need some help, please let me know. Okay, but we do not need to fear buffer questions. Okay, and if you do still fear them, drop me a message and we can see what we can do to help. Okay, hope you're all having a good day, or as good a day as possible, and I still hope that the revision is going well. Take care, guys.